All right, let's go and get started. Let me get the lights and whatnot adjusted a little bit. What's it? Oh. I wanted to go through something real quick. I know it's been a long time since you all have done this homework, but this is going to start to influence things a little bit on your project. And that is this homework, the homework where you did the live load distribution factors and all of that. I finally did get it graded, and I've posted all the grades to Blackboard. But there's a couple mistakes that I wanted to illustrate across the board. Okay, number one is in relation to the lever rule. So, okay. I just wanted to go ahead and write this out. So for the lever rule, when you do your truck placement, this is what you do. So you've got your barrier that's kind of something about like that, right? And it's going on. Okay, you're going to have a truck that has half of its wheel right here and half of its wheel right here, right? So this is a half and this is a half, okay? When you place that truck on the bridge, you place it so that this distance is 2 feet or 24 inches, okay? This location is independent, in terms of where the exterior girder is. You could have the exterior girder there. It could be here. It could be anywhere. I think what a lot of people were doing, hold on. I think what a lot of people were doing is they were placing this half that truck. They were placing it right where the I-beam was. Okay. So this distance right here didn't end up being 2 feet. It was like 30.5 inches or something like that. Now, this truck is always placed 2 foot from the barrier. What ended up happening in the example that we did in class is 2 feet from the barrier just so happened to put that load right under that exterior girder. So this load is always 2 foot from the barrier, and it's independent of where the girders are. It doesn't really matter. Okay, does that make sense? Everybody have a question? Any questions about that? Okay, now the other thing I will point out is the distribution factor for deflection. Okay, so this bridge had 3 lanes, okay, and it had, I think it was 5 beams. Wasn't that the case? I think it had 5 beams and 3 lanes. Okay, and what a lot of people did is they said, okay, the distribution factor for deflection is the multi-presence factor times, 3 over 5, which is 1 times 3 over 5, which is 0.6. Okay, and that's wrong. And the reason why is this. Okay, your multi-presence factor for 3-lane loading scenarios isn't 1, it's 0.85. Okay, so your answer to this was 0.85 times 3 over 5, and I think it was something like 0.4 something like that. Okay, that's the 2, I think, big mistakes that kept popping up. See, this lever rule analysis, if this was incorrect, it affected all your moment and shear distribution factors for 1-lane loaded exteriors. So that it wasn't a big deal, but it did pop up here and there. And the only other thing I would point out, which I think this was a mistake in the lecture notes on my part, so I didn't take off any points for it, but I want to pull this up real quick. So, okay, so if you go to here, you have moments and shears and whatnot, okay, and you have to distribute those. Now, case 1 and case 2 was 1.33 times the truck plus the lane and 1.33 times the tandem plus the lane. I had a mistake in my when I did this in class, and I think I put a comment on the video, but if not, no big deal. I didn't take off any points. But this is 90% of 1.33 times the double truck plus the lane, The same thing was true here. It was 90% of 1.33 times the double tandem plus the lane. When I did this in class, I think I was in a hurry and I kind of forgot that 0.9. And a lot of people, when they were doing their homework, were following the video and they didn't put the 0.9 either. So that was probably a little on me, so I didn't take anything off for that. But all in all, that was it. Other than that, I think everybody was pretty straightforward and did pretty well on it. So let me say changes to that. So I know it's been a little while, but does anybody have any questions about any of this? Because this stuff is going to start to creep up again, because with your design project, I mean, think about how this design project is going to go. You need to size a girder such that the resistance is larger than the loads. Well, in order to determine the loads, you need the section properties, you need the dead loads, you need the live loads, which means you need all of this. So this stuff is going to pop back into the fray. So I wanted to see if anybody had any questions or if you're all good. Mm-hmm. Eccentricity, which eccentricity? Oh, the E value. Yeah. That's very possible. Okay, a couple things. Let me answer that in a little bit of a larger context. Okay. Let me extend this. So the question was, can you get an eccentricity that's negative? And the answer is yes. Now for the lever rule, what you can have is this. So let me draw this out a little longer. Okay, so let's say you're doing a lever rule analysis. So here's your barrier and here's your deck. So you're going to have your truck placed somewhere about like this. Okay, so here's this and here's that. Okay, so let's say this is 1/2 and this is 1/2 and this is 2 feet from here to here, and this is 6 feet from here to here. Sound good? Now, it is possible when you look at your girder layout that you have a girder layout that looks something like this, that you have, you know, an I-beam here, and then you might have an I-beam that's here, okay? So this second point load, this second half of the truck actually falls outside, okay? Now, the way that you handle that is, you know, keep in mind what you're doing. You're turning this essentially into a roller, you know, right there, and this is kind of a hinge, right? So what you're doing with the deck right here is you're doing this. So, you know, you've got a situation that looks like, oh, you've got a situation that looks kind of like that. And you've got that, and then here's your hinge. Make sense? So if you've got this situation with the lever rule, the question, well, are you going to get a negative eccentricity for this load? Well, yeah. But I guess the bigger question is, if you're assuming that this is a hinge and putting this truck on here and trying to figure out this reaction, I guess the bigger question is, do you even consider that load? And the answer is no. So you would just look at the dimensions and say, okay, this wheel is going to go on this side, and if I'm trying to determine this reaction, I'm not going to worry about it. So in this regard, you would just disregard that. Okay, now that's for the lever rule. For for special analysis, it's a little different, because for special analysis, you're looking at the whole bridge rotating. So this, I believe, had 3 trucks on it. I think there were 3 times you did special analysis. So you might have something that looks like this. Something about like that. And I think there were 5 beams. There was something like this, something like that, like that, something like that, something like that. Okay, so the center of those girders, you know, falls kind of like that, right? And you're measuring those eccentricities from that center line of the pattern of girders. So your first truck might be, you know, right here. So like here's your first truck. This is truck 1, right? So the distance from here to here, that's E1. Make sense? Okay. E2 is going to be similar. You know, you're going to have a truck right here and a truck right here. So that's truck 2, and then maybe I ought to squinch it up a little bit. That distance right there, that distance is going to be E2. Make sense? Now, both of these are taken as positive because the idea is that in special analysis, what you're doing is we're really focused on looking at that girder right there. So we're trying to determine, you know, what's the reaction here with these trucks. Now, it's very possible for your third, you know, your third lane, your third truck, that you might have a truck that's somewhere over here. So you might have, you know, truck 3 right there. And in this case, that would be your E3, but it would be negative. Does that make sense? So this would be a positive E1, a positive E2, and a negative E3. So if you want, you could look at it like this. So for one lane loaded, your sum of E's would be E1. For 2 lane loaded, your sum of E's would be E1 plus E2, and for 3 lane loaded, your sum of E's would be E1 plus E2, if you want to think of it, minus E3. Because the idea is that other truck is sort of serving to rotate the bridge the other way, so it's softening the reaction on that exterior girder. Does that make sense? Well, that's basically what I'm saying here. No, because what you're doing in this circumstance is you're trying to assume that the whole cross section rotates. So you've got to consider it. I mean, I guess the worst case scenario would be considering that it's 0, but you're kind of already doing that here. You see what I mean? Because in the 2 lane loaded scenario, it's not there. Does that make sense? So you've kind of already considered that. Now, let me also say this. I mean, let's also get practical about it. If I go through and do all of these, I mean, what's the point of doing, you know, this analysis, and this analysis? The point is to get a distribution factor, right? So I'm going to get a distribution factor here, I'm going to get a distribution factor here, and a distribution factor here. And the point is, when you're doing the design, to use the largest one. Now, I'm going to take a wild guess and say that one of these two is going to be larger than that one. You see, so in the end, I don't think it's really going to matter. So, does that make sense? This is good stuff. Any other questions? Did I answer yours? Okay. Okay, all right. Is that good? Any other questions? Okay. Now, last time, I do sort of want to somewhat sort of want to pick up from where we left off last time. Last time, if you recall, we had a marathon of calculations that we did, and we were calculating values after values, and it seemed like it never ended. Well, I want to use that stuff today with a little bit of purpose, okay? So all that crap that we calculated last time, I want to make sure that it makes sense. So I want to go back to this real quick just to sort of get back into the mindset of what it is that we're doing and what the point is. Remember, the point of everything that we did last time and all the math that we did is we were trying to determine how strong these girders are in their non-composite state. Because we've already looked at determining phi mn for their composite state, but we haven't looked at non-composite states, okay? Which is important, A, for negative bending regions, and B, when we're looking at the bridge during construction, which we'll look at constructability calcs later. And you'll see how there's going to be like a phi mn or a phi f sub n. And it'll, at that point, be like an afterthought to us because we'll already know how to compute it. Okay? So right now, the point is to try and go through those calcs and make sure we understand it. Okay? Now, just to recap so that everybody's clear on what's going on, remember, phi is going to be 1 for everything that we do. And our big push is to try and assess whether or not we're dealing with a beam or dealing with a plate girder. Now, again, you learned this last time. The formulas are a little long and they can get a little nasty, but in the end, they're very plug and chug. Once you set them up in Excel once, you don't have to do it again, okay? So they're very easy to Excelify, quote unquote. Okay. And of course, you've got the flow charts and whatnot if you want to follow along there as well. Now, and I'm going to skip through this a little bit. So we started off looking at composite girders, which is what we've already done, and we learned a little while back how to compute Mn, and then just take this and multiply by 1, so phi Mn for a composite girder. And that's pretty straightforward once you've got MP. Now, we also have a ductility check, which is pretty straightforward. I'm going to move past that. For non-composite girders, we have to determine whether or not we're dealing with a plate girder, which is governed by 610.8, or whether we're dealing with a beam section that's governed by Appendix A. Remember, if we're dealing with plate girder sections, we're going to see our capacities listed in terms of stresses. You know, the bending stress has to be less than or equal to phi Fn, a stress capacity. If we're dealing with beams, we're going to be looking at moments. You know, Mu has to be less than or equal to phi Mn. Okay. Now, last time we went through and categorized our girder that we were looking at for our example, and we found it was in fact a beam. It was an Appendix A section. Remember, it was a really stocky, short shape. So we were allowed to use Appendix A. So let me go forward a little bit into the Appendix A calc so that we can kind of get an appreciation of what's going on. Remember, while the formulas might get nasty and get hairy, this is what we're talking about, okay? And I know my steel folks who've seen this before, this should be old hat, you know? Remember, we have our plateau region, inelastic buckling, and elastic buckling, modified by a moment gradient modifier C sub B. That's the long and short of it, and all these equations are still representative of that. They may be a little hairier and a little nastier because we're dealing with plate girders as opposed to beams that are singly symmetric, and we have to go through and calculate all those properties that the steel manual just laid out for us in a lovely fashion. But in the end, the behavior is still the same. So I'm going to skip ahead. I'm going to skip past the 610.8 stuff because we already did the math that showed we're in Appendix A. So let's skip past all this 610.8 stuff. So Appendix A, okay? So if you're in Appendix A, the first thing you have to do is compute a set of Webplastification Factors, RPC and RPT. Basically, they are a measure of how much you can get above My, the yield moment, okay? Now, the way that you compute those is as follows. The first thing that you do is you compute a bunch of starting values. But take a look at all this. We've got web slenderness. Remember this? Lambda P sub WD sub C, lambda P sub WD sub CP. This is the stuff that we grunted through last time, the stuff we've already computed, right? Remember, we went through and did all these calcs over and over again. That was the point, so that all this stuff, all this grunt work was done and over with, okay? So the idea is this. Now we can start making some decisions. Now, the way that we compute, here's some more starting values and whatnot, which, again, we've already computed. Now, here's the deal. We look at our web slenderness, and we compare our web slenderness to this limit, this plastic web slenderness limit. And the idea is if we have a fairly stocky web, then the idea is theoretically we could hit MP. If not, it's a linear fit away off of MP, you know, a linear interpolation off of MP. Plug and chug, okay? Look at a lot of these values going into this. Lambda PWD sub C, lambda PWD sub CP. We've already computed all of this. That was the whole point from what we did last time. Make sense? So hopefully there's a little bit of purpose behind all that crap that we did last time. Okay. Now, once you've got your Webplastification factors, we have two limits we're going to assess. Local buckling of the flange and LTB of the whole shape. Local buckling of the flange, we have a number of starting values we got to do. Again, we've already computed all this intro stuff, all these starting values. And here's the deal. Local buckling of the flange is guarded by, or is predicted by the Webplastification factor times the yield moment if you've got a fairly stocky flange. If not, linear fit off of that. And again, all those values we've already taken care of. For lateral torsional buckling, very similar. Okay? We need our unbraced length, which is where our cross frame spacing. We need the moment gradient modifier, which we already did all that, and I posted that calculator that could do that for you. C sub B for this unbraced length that we did was 1, okay? And if you want to be conservative, C sub B can be taken to be 1 across the board. I don't recommend it. You know, all C sub B is going to do is take your capacity and make it larger. So if a little bit of math can increase your capacity, use it. That's what it's for, okay? Now we need our anchor points for the LTB curve, which we've already computed, reduced yield stress, and all of our properties. Again, that was the whole point of all that grunt work we did last time. We already computed all of that. And here's the long and short of it. This equation that you're seeing right here, this right here is that, okay? A plateau region, linear hyperbola, okay? Zone 1, Zone 2, and Zone 3 for LTB. Let me go back to that slide. Here you go. Plateau region, a constant capacity, which this is essentially MP or close to it. MP, a linear fit off of MP, or your LTB expression. And this expression, I mean, anybody who had me for steel design should know, that should be somewhat familiar from steel design. All right. And that's it, okay? So I know last time seemed like a marathon, but the idea was to do all that grunt work, okay? So let's go back through that just so everybody's clear on what we did, okay? So now, the big thing in this calculation that you have to keep in your head is we're looking at non-composite capacity, okay? So since we're looking at non-composite capacity, that concrete deck, it doesn't exist, okay? All right? And that's important because later on we're going to look at deck casting. We're going to look at constructability. When we pour that wet concrete onto that girder, the girder by itself has to resist those forces, okay? Now, here's our dimensions for our girder and positive bending, and here's our section properties that we know how to compute. The first thing that we did is we determined whether or not if A6 applies, Appendix A, which we found out it did. It was a pretty rote calc. And then we got into it. First thing we needed were elastic section properties. Remember, our section modulus comes directly from the spreadsheet that we did way back in the beginning. So we can get yield moments. Yield moment for the compression flange, yield moment for the tension flange. Quick pop quiz. If you're going to do any calcs that reference MY, which one do you use, MYC or MYT? The smaller one. There we go. All right. Got everybody on that. We need plastic section properties, so we've got to compute MP. We can use that same appendix, but remember we set not only the rebar terms equal to 0, but the slab term equal to 0 as well because there's no slab. Once you get that, very plug and chug, go through that, we get MP. Now, D sub CP is the depth of the web in compression at the plastic moment, which for this case is Y bar, and it comes out to be 31.857. Again, all non-composite. Then we've got remaining properties, okay? And I know this seems like a laundry list of stuff, but in the end, it's all plug and chug. So we went through, let me scroll through all this. So we went through and computed R sub T, which is the radius of gyration for lateral torsional buckling. We computed this reduced yield stress to account for residual stresses in the section after welding. We computed J, which is our torsional constant. H, which is the distance from the center of the top flange to the center of the bottom flange. Think of that as kind of a moment arm between those two flanges. Our anchor points, L sub P and L sub R, those are the anchor points for that LTB curve. Remember, when you do LP calcs, go through and plug and chug, they're going to come out in inches. So make sure you convert if you need to. Either convert your cross frame spacing into inches or convert these into feet. It doesn't really matter as long as you're consistent. We computed a host of slenderness limits, slenderness limit for the web, anchor points for the web slenderness, R sub W and P sub W. Again, plug and chug. We computed the flange slenderness, and then our plate buckling coefficient to get lambda sub P and lambda sub R anchor points for the flange. Sound good? So everything that we do from here on out is just going to reference stuff that we already calculated. Everybody okay with this? All right. All right. So since we're in Appendix A, okay, the first step in Appendix A is to compute Webplastification factors, okay? Oh, goodness, my cord's getting all tangled. So Webplastification factors. So I'm going to need y'all's help on this to ensure I'm pulling all the right values. Whoop. Okay, so RPC and RPT. Okay, so the first thing that we've got to do is compute an actual web slenderness value at MP. So what we've got to do is compute 2 DCP over TW, okay? Now that's 2 times, if memory serves me correct, that was 31.857. Is that what DCP was? Okay. Over the web thickness, and this web was, what, 7/16 or a half? 7/16. 7/16. Okay. When you plug and chug, that gives you a web slenderness of about 145.63. Okay. So that's a measure of how slender that web element is at MP, if you want to think of it like that. Okay? Now I'm going to compare that against the limit. Okay? Now the limit is lambda sub PW at DCP. But guess what? We already computed that. And if I remember, we computed that and we got a value that was like 64.28. Does that make sense? Isn't that what we got? Or 64.284 or something like that? What did we get? 284. All right. Make sense? Okay. So we use these to make a decision as to how we compute our web classification factors. So if you think, this is a measure of web slenderness, this is our limit. So we're not really dealing with a super stocky web in this scenario. It's much more slender than the limit. Does that make sense? So we're not able to get all the way up to MP. We've got to back it down a little bit. So I'm going to hop back and forth between the PowerPoint a little bit because I want to make sure everybody's following along. So here's our equations for web classification factors. And if this limit is less than or equal to, or if this slenderness is less than or equal to this limit, here's your RPC and RPT. That would have been nice, but we're not quite there. We got to calculate this. Luckily, it's all fairly plug and chug. Okay? We've got our hybrid Gerber factor, which is 1. We know MYC and MP, and we have all of these computed. So in the end, it's all fairly plug and chug. Everybody okay with this? All right. So I'm going to do RPC, and then we'll just write down the answer for RPT because it's a pretty similar formula. So therefore, RPC is the following. It's the minimum of. Okay? So it's 1 minus quantity 1 minus RH MYC over MP, and then lambda sub W minus lambda sub PW DC, lambda sub RW minus lambda sub PW DC, and all of that multiplied by MP over MYC, and that's one term. It's the minimum of that and MP over MYC. Okay. So 1 minus. 1 minus. I promise that's not a typo. Okay. Our hybrid girder factor is 1.0. Our MYC, what was MYC? Does anybody remember that? I think it was 2558.4 foot kips over MP, which was 3326.3 foot kips. So far, what's going on with the units? Well, what's happening? We've got foot kips over foot kips, right? What the heck's going on with my eraser? All right. All right, now we've got lambda sub W, which is, what was that, 115.46 minus lambda PW at D sub C, which was 50.97. Isn't that what it was? Ooh, my computer's getting a little slow on me. And then lambda sub RW, 137.27 minus 50.97. So notice what's happening with the units. Everything's canceling, all right? And then we have MP over MYC, which is 3326.3 foot kips. And then we have 2558.4 foot kips. So all of that will give you a quantity. The other term is just 3326.3 foot kips, and then 2558.4 foot kips. So it's going to be the minimum of all of this, and then all of that. So what does the blue term come out to be? What's the first one? 1.0158. Is that what you got? 0.75. So maybe 0, because it's 0.758, maybe 0.76. Something like that. And then what's the other term come out to be? .3 something, whatever it is, it doesn't matter, because that means that RPC is 1.076. Make sense? Now, RPT is calculated the exact same way. Instead of dealing with MYCs, we deal with MYTs. So it's literally the exact same thing. If you go through and do the math, you're going to find that this comes out to be 0.90. So if you want, I can go through the exercise, but literally replace your MYCs with MYTs and plug and chug. Everybody okay with that? All right. Any questions? Not too bad. Okay. So what this is telling us is that our compression flange is able to get above MY a little bit, about 7% above MY in the worst case scenario. It might not seem like a lot, but when you're talking about some of these substantial moments, every little bit helps. Okay, so again, if all it took was a little bit extra math and you could shave, a 1/4 of an inch of flange thickness, that's going to save you some money. do it. So, okay. All right. Okay. So we've got two capacities that we've got to assess. The first one is compression flange capacity in local buckling. So let's see, compression flange local buckling. All right. So what I want to do is I want to pull three numbers, okay? I want to pull lambda sub f, and then I want to pull lambda sub pf and lambda sub rf. So you all do a little bit of digging. You tell me what each of these values are. Nine point what for the first one? 9.33. What about these two? 9.152. And then this one is, say it again? 17.47. Okay. So just so everybody's clear on what's going on, here's what we got. Okay. I'm going to go back to the PowerPoint. I'm going to refer to this image quite a bit. Okay. So what we're looking at is the capacity, okay? Now, this line sub right here, or this value, that's lambda sub PF, right? Lambda sub PF was what, 9.17, something like that? This is lambda sub RF. It's 17.4 something, right? Now, our value is 9.33. So we fall somewhere right there, right? So that means we're in zone 2, and we've got to use that linear regression, right? Make sense? Okay. Okay, give me a second. All right. If I scroll past in Appendix A, and I look at flange local buckling capacity, here's the expression, okay? If I'm in zone 1, it's that plateau. It's just RPC times the yield moment. If not, I'm in that zone 2, and I use this. Again, just a linear equation, okay? Make sense? And everything in here, we know. We know all our lambdas. We just wrote them down. We know what FYR is. That's our reduced yield stress. We know what our section modulus is, and we just calculated RPC. All right? Make sense? Any questions? All right. So with that, this is a pretty basic calculation now that we've got all the stuff that goes into it. Okay? So I propose we're in that second range, and therefore the nominal moment capacity in compression, and if you want to put flange local buckling to indicate we're looking at the local buckling capacity, is the following. Okay? It is 1 minus a fraction. That fraction is FYR SXC over RPC times the yield moment. I might have to jump to another sheet here because I'm starting to cut out on this one. I think this set of calculations just got too long for this computer to handle. Lambda sub F minus lambda sub PF, lambda sub RF minus lambda sub PF, RPC MYC. 1 minus. So let's start plugging and chugging. FYR was what? That was, wasn't it 35 KSI? $35 KSI. Now SXC, that was that section modulus, the one on compression, and I think that was 614 cubic inches, right? All right. RPC, we just did that, was 1.076. Now, yield moment. What do you think, what's going on here? What value do we need to use for our yield moment? Well, looks to me like if everything's in inches, we need to throw inch kips into the mix, right? So that means for this we need to use 30,700.7 inch kips. Everybody see that? This is where writing those units out really helps out, because it'd be tempting to just use foot kips. Now you got to be careful. All right. Now our lambdas, we have 9.33 minus 9.152, 17.47 minus 9.152. Okay. RPC is 1.076. Now, might seem a little strange, but I'm going to go ahead for my yield moment right here and use 2558.4 foot kips, because inside the expression I needed that to be an inch kip so that everything cancels, but when this is all said and done I still want my answer in foot kips, so I might as well just use that. Now when I plug and chug, I get that the nominal moment capacity for flange local buckling is, let me find it, 27, there we go. All right, mine came out a little lower. I think it's probably because I was tracking decimals. I got 2731.5, but close enough. Foot kips. Everybody okay with that? All right. Any questions so far? Okay, so that's one nominal moment capacity. We got to compute the LTB and see which one's lower. All right. So let me go ahead. I need a new sheet just because I'm running out of, it's starting to cut out on me. Okay. So last one, we need compression flange LTB capacity. Now here's what we do here, okay? We need the unbraced length, which, what is the unbraced length? That's the cross frame spacing, right? Anybody remember what that was? Remember, if you go to this, you go forward, remember, here's our girder, right? And here's our deck and whatnot. But if you look at the framing plan, remember, here's the abutment, there's the pier, and then there's the other abutment, and we're looking in positive bending, so that cross frame spacing is 20 feet. Everybody okay with that? So the cross frame spacing is 20 feet. Now, we need our anchor points, okay? So what's LP and LR? Anybody remember what these are? They're in there somewhere. I know we did them. So 74 inches. What is it in feet? Since everything's considered 6.98, something like that. 6.98 feet. And what was LR? Okay. Everybody okay with this? Okay. So if you look at this, let me go back here to my familiar image. Okay, so look at this. It's the same story, okay? That's LP, right? And it's what, 6.98 feet? This is LR, and it's 28.36. We are dealing with a cross frame spacing that's 20 feet. So we're somewhere about like that. And we're still dealing with that linear fit, right? Same story, okay? So what's the scenario? Well, let me erase all that, or that's going to get stuck. Okay, so what's the story? Let me scroll here towards the end. And here's our expression. So here's the LTB capacity of that flange. Zone 1, it's just that constant value. Zone 2, linear fit. Zone 3 is that hyperbola, okay? Everybody okay with this? It's the same story. The equations are a little messier because we're dealing with a singly symmetric section. In the end, it's all the same story though. So, now, one other thing we're going to need is C sub B, but we've already computed that, and that's 1, okay? Oh. Okay. So, if you've got C sub B or equals 1, then here's your capacity. See, usually your capacity is as follows. It's usually MNC equals the minimum of C sub B times some formula or RPC MYC. But since we know C sub B is 1, I can tell you that the answer is just going to be whatever this formula is, which in this case is 1 minus FYR SXC over RPC MYC. Again, everything probably should look pretty familiar. The only thing that changes it is we're not interpolating with respect to the flange slenderness values. We're interpolating with respect to those unbraced lengths. So it's, oh, wrong one, getting ahead of myself. LB minus LP, LR minus LP. And usually for an economic design, you want to be in this zone 2. Zone 2 is usually where you get most of your economic designs from. Zone 3 gets a little slender and a little wobbly. Zone 1, you end up using quite a bit of steel. So, and everything you're seeing here, this is that formula that I'm talking about. Usually it's the minimum of CB times all this or RPC MYC, but since CB is 1, I know this is the case. So 1 minus 35 KSI times SXC, which was 614.01. Then we've got RPC, which came out to be, I think it was like 1.076. MYC was, in inch kips, 30,700.7 inch kips. Now, instead of the flange slendernesses, we're using our unbraced length, so 20 feet minus 6.98 feet, 28.36 feet minus 6.98. This is where the linear interpolation happens right here. And then 1.076 times, what is it? Since I want to have my answer in foot kips, might as well just use 2558.4 foot kips. And what I should do is I should put LTB. I should change that up here as well. MNC for LTB. All right. So, anybody got an answer? What'd you say it again? 1090. See, Mine's a little higher. I got 1790, 1790 point. I got this, 1790.8 foot-pound or foot kips. Did anybody get something like that? Maybe it's on my end. Anybody get anything? Anybody, you didn't get this? Yours is way out. Okay, hold on. Let's break out the Excel and let's check it and make sure everything's fine. What? all right. Hold on. Are all the values going into it right? This is 35. That's 614.01, 1.076. I think all the formulas or the values going into it are right. All right. Let's break the Excel out. Yeah. Yeah. All right, hold on. Let's just check it out. Okay. All right, so that's the calculation we need to do, right? So we have, all right, 1 minus. We have a fraction that has 35 times 614.01 divided by another fraction, or divided by a quantity 1.076 times 30700.7. Okay, so that's that times, let's see, what do we got? This 20 minus 6.98 divided by 28.36 minus 6.98. That's all that times 1.076 times 2167. Why? How did I get? What's that? Yeah. Wait a minute. I think I know what I'm doing. Hold on. Let's do this. I think I'm shortcutting it here. I think that's what I'm doing. Maybe what I should do is be a little more diligent with it because I have the whole thing typed out. What is RPC times MYC? Is that it? No, that ain't gonna be it. That ain't it. Because that's this right here, and that's going to be larger. Okay. What did I do? So, say what you were saying again. Because I've got it typed in right. But, oh no, I don't. I have an error on here. You all are right. This is correct. I'm sorry. This is 2167.0. I'm sorry. You all are correct. 2167. Because on mine, I have a typo. I have that is LB. That was a typo on my part. Whoops. I'm allowed to make a mistake here and there. Okay. So this comes out to be 2167. You all were correct. I was wrong. All right. Everybody okay with this? Okay. So the last thing I want to do is this. I want to do tension flange yielding, which is really simple. All it is the moment capacity of the tension flange is RPT MYT, and that's it. So it's just, this was 0.9 times MYT, which comes out to be, or we already did that, that was 3697.9. 97.9 foot kips. And that comes out to be, say it again, 3328. 3328 point what? 1. So 1. Yeah, that's about what I got. Okay. So, to summarize this long series of stuff that we have done, here's the long and short of it. Okay, so summary. All right. So we have an MNC for the compression flange in local buckling as, what did that come out to be? We know what this one is. This one is 2731.5. This one's 2167.0 foot kips. And then MNT was 3328.1 foot kip. All right, so to summarize what's going on, keep in mind that phi is 1, so phi is 1. So to summarize, this is the capacity, this first one, that's the capacity of the compression flange in local buckling. So do you remember that video when we had the girder and we were they were loading the girder and the flanges started to crinkle? By themselves, the flanges started to buckle. I propose that for this girder, that's going to happen at 2731 foot kips. But what's going to happen first is this. The compression flange is going to experience lateral torsional buckling before that happens. So if you want, the nominal moment capacity of this compression flange is going to be the lower one, the 2167.0 foot kips. And the capacity of the tension flange is 3328.1 foot kips. So if you want a big answer, if you will, to what we've been doing, it's this. Okay? So what I'm getting at is this. This is sort of the whole point. That girder by itself can resist a moment of 2167 foot kips if what I'm looking at is the compression flange. If I'm looking at the tension flange, it's 3328.1. Now in actuality, if I start loading this girder, the compression flange is going to fail before the tension flange does. The reason why I'm keeping them separate is because there's different stress checks on different flanges, so you might as well keep it as is. Does that make sense? Now, let me ask you a question. Let's just use our noggins a little bit. Do we think that girders, just in general, should be stronger compositely or non-compositely? Where should we see the larger strength? Compositely, right? Now I want to take us back a little bit, okay? I want to take us back a couple weeks. All right? Do you remember this when we did the strength limit state and we calculated that, phi mn? Look what we got. We got a phi mn of 6,315, something foot kits, right? Think about that. That is the capacity of the girder in its composite state. And compositely, it can hold up a whole heck of a lot more bending moment than it can non-compositely, right? See what's going on here? So the effect of that concrete deck is pretty pronounced. But on the flip side, you got to think of it like this. Once that girder is composite, it can hold up what? 3 times the amount of load? That sucker's stout, when it's composite. But what about when you're pouring the deck? It's pretty weak, comparatively, right? So we got to think about that. Okay? Does that make sense? So what I want you all to do, and this will be due next week because you all have the homework, I want you to write a spreadsheet that can compute these numbers. Okay? And then what we'll do is, over the next couple weeks, is we'll start using them. Okay? Now you already know how to use this, okay? Because you can take this, compare it against your moments to determine a factored moment, and see whether or not your girder is okay, right? Okay, so you all can do that math, and you should be preparing to do that, okay? What I want to spend the rest of tonight talking about is 2 things, and we'll take a little bit of a break after this. We're going to dabble a little bit into shear tonight, because I want to spend this week, and I want to basically next week to be the shear week, to sort of get shear out of the way, because we haven't really talked about that. But I want to talk about just girder design in general. I mean, going to this, let me pull this up real quick. Go into this. So here's our example. And look at this. We've got a, goodness, there we go. Sit still. All right. So here's this. We got a top flange that's 14 inches wide and 3/4 of an inch thick. And we got a web that's 42 inches deep. Where in the heck did they come up with those numbers? Where the heck did they come up with that? All right. Well, I'll tell you how they came up with that. They wrote a big Excel spreadsheet, and they started twiddling around with the plate dimensions and plate sizes until they got something that made sense. But they had to start with something, right? They had to start with a girder size that made sense. And that's what I want to talk about after this, is how do we come up with that trial size at the beginning, and how do we tweak accordingly? And I want to talk about tweaking. How do you tweak those numbers efficiently and economically? But we'll get into that here in a second. Let's take a little bit of a break and get back together, what, 7:50, something like that? All right.